Welcome to NPTEL online course on fractals and multifractals. So, in the previous lectures, we have discussed how to construct the deterministic fractal in a metric space. In summary, we have defined the Hutchinson-Bansley mapping, and the deterministical fractal is defined and constructed by using the iterated function theory. A deterministic fractal is constructed as a unique non-empty invariant compact subset of a complete metric space by using the Banach fixed point theorem. In the last lecture, we have discussed what is the classical interpolation and what are all the drawbacks of classical interpolation. While coming for the real life scenarios, classical interpolation functions provide the smooth approximation even though the data points are highly irregular data. So, we need to construct the finer approximation for the given set of data point. In order to rectify this problem, Professor Bansley introduced the fractal interpolation. The fractal interpolation function will be constructed using iterated function system theory. So, in which we need to find one continuous function which passing through the given set of points. If you find the graph of the continuous function, it should be the unique non-empty compact subset of a complete metric space. So, in order to that, we need to construct the proper iterated function system to generate the fractal interpolation function. So, in this lecture, we are going to discuss how to construct the proper iterated function system to generate the fractal interpolation function. So, this upcoming weeks we are going to discuss constructing the iterated function system to generate the fractal interpolation function, and what is the effect of scaling factor in fractal interpolation, and what are the different type of fractal interpolation functions are available, and the calculus of fractal interpolation function, that means the integration and differentiation of the fractal interpolation functions. So, let us start with the classical interpolation. A classical or a process to estimate the function f from the interval a comma b to r at any given point x belongs to closed interval a comma b, such that whose graph passing through all given finite number of points which partition the given interval. So, the interpolation, a process to estimate the function of f from closed interval a comma b to r such that some finite number of points will partition the given interval. This function f must passing through the given set of points. Then, what is the advantage in classical methods available in the literature produces sufficiently smoother interpolation to approximate the unknown values at a given set of points. There are different methods are available to generate the classical interpolation, whereas many significant real world phenomena including the climate pattern, EEG signal shows higher irregularity when it plotted, where the classical method failed to depict their fine geometric pattern. Therefore, we need some better tool. The requirement of non-differentiable interpolants exposing complex pattern motivated Professor Bansley to introduce the concept of fractal interpolations. So, let us discuss how to construct the fractal interpolation in this lecture. Let us discuss the construction of proper iterated function system to generate the fractal interpolation. Let a set of data points xi, yi belongs to R power n be given such that xi is strictly less than xi plus 1 for all I belongs to n minus 1 and not necessarily equidistant. What it means? Suppose we have the interval like this one x1, the x1, x2 are strictly increasing, whereas xi minus 1 and xi plus 1, if you finding the distance between these two intervals, it need not be equal distance. So, it not necessarily equal distance. So, x1 maybe x2 here, x3 here and so on. We can find this is xn minus 1, this is xn. So, the x1, x2, x3, if you are finding the relation, x1 is strictly less than x2 and x2 is strictly less than x3 and so on. The data points are not necessarily equidistant. Okay. Then for each xi, we have the corresponding yi values. That means this data set xi and yi is given to us. So, for x1 corresponding with some y1 and x2 is corresponding with y2 and x3 is corresponding with y3 and so on. This is maybe x y n minus 1, this is yn. So, now we have this type of data set. So, here in this data set one can understand that we can take x1, x2, x3, that xi's are equidistant or not equidistant. We can take the different interval also, we are constructing the IFS. Then for each I belongs to x1, for I here we are defining I as the closed interval x1 xn. That means if we have the data point here x1 to xn, take this as a closed interval, that is our I. Then II is each sub interval, maybe I will take like this one. So, this is x2, x3 and this may be etc. This is xi minus 1, this is xi, this is xi plus 1 and so on. So, I denote xi xi plus 1, that means each sub interval we are denoting as II and the whole interval we are denoting as x1 to xn. Note down, if the number of data points is n number of data points, we have n minus 1 sub interval. For example, if you are taking 0 and 0, 1, 2, 3, this data point is given, then I equal to closed interval 0, 3, whereas I1 is this one, I1 is 0, 1 and I2 is 1, 2 and I3 is 2, 3. So, that given data points, for I am speaking only about the xi, because each xi we have the unique yi. So, here if the data point in the sense there are 4, each xi is corresponded with yi. So, here the 4 data are given. So, we have 3 number of intervals, sub intervals. So, this whole interval is we denoted as I and each sub interval we are denoting as II. So, therefore, this I varies from n minus 1 number of points, n minus 1 number of points. If we take the number of data as n data. So, if we have the data as x1, x2, so y1 and x2, y2 up to xn, yn, first n number of data points, then the number of interval, subinterval, we need n minus 1 subinterval, n minus 1 subinterval. Okay. Let us define Li is a mapping from I to Ii. So, Li is a mapping from the whole interval to the subinterval. Maybe I can write it here. So, our I is x1 to xn, x1 to xn closed interval, then Ii is xi and xi plus 1. For Li is defining from I to Ii be homeomorphism such that it satisfying this equation 1. That means Li of x minus Li of x dash is less than or equal to Ci times x minus x dash. In the sense Ci we are taking from the closed 0 and open 1. So, in the means Li is a contraction as well as the homeomorphism. So, we are defining n minus 1 contractive homeomorphism from I to Ii. So, what it happen from if you are taking L1, L1 is a function from x1 to xn, this is the domain, and the codomain we are getting x1 to x2. The whole interval, this whole interval we are just compressing to the this interval Li from I to Ii, which is a contraction, therefore, it will contract to the first interval and it is a homeomorphism. So, 1 1 on 2 as well as the Li is continuous. If you are finding the inverse of Li, that Li inverse also continuous function. Now, we need to check whether this type of mapping will existing for I and Ii. Between this I and its subinterval, is it possible to find the such a mapping, so that we can assume that there is a mapping. If there is no existence, we cannot assume that the function is existing. So, let us check whether such a function will exist. Also, before that, this Li will satisfying the endpoint condition. So, I will back to this endpoint condition again. First, let us check such a function will be available. See, the homeomorphism Li from x1 xn to xi to xi plus 1, that means this whole interval to the subinterval is given by this equation. So, now let me explain how this equation will work. You can take the interval xn to x1 to xn and assume that this is our xi and this is our xi plus 1. Now, Li is a function from x1, the closed interval x1 and xn to the closed interval xi comma xi plus 1. We need to check such a mapping is existing. So, for that this point must move to the xi and this point must move to the xi plus 1, then all the remaining points should be inside this interval. So, that this endpoint condition will satisfy, that is the endpoint condition. What is the endpoint condition? Li of x1 equal to Li of x1 equal to xi and Li of xn, which maps to the endpoint of the subinterval. That means, for each I, if you are operating the function L on the initial point, it must map to the initial point of the subinterval. If you are operating on the end point xn, it must map to the end point of the each subinterval. Now, we need to find whether such a mapping Li is existing in between these two intervals, the whole interval as well as the subinterval. Now, if we are finding the line joining between these two equation, that means 2 point we can take x1 and xi and xn and xi plus 1. For line joining these two equation, x minus x1 over x2 minus x1, x2 minus x1 equal to y minus y1 is xi over y2 minus, this is y2 minus yi. So, from this thing you can find the y. So, one can get the ys, you can just cross multiply. So, one can get xi plus 1 minus xi over xn minus x1 times x minus x1 plus xi. This you can take, you can get xi. So, this is the equation we are getting here. So, this we can call it as Li of x, because it is just line joining two equation, then it is a 1 this is just compressing this element to here and this element to here. Then by using this one can construct the mapping Li from the whole interval to the subinterval. So, in which if you are taking A is this one, this xi plus 1 minus xi over xn minus x1, then one can get Li of x in the form of ai x. So, Li of x equal to ai x, one can need to chase ai is like this one. Then if you want to find the other term, just we can simplifying this one, Li of x can be written as this one, xi plus 1 minus xi over xn minus x1 and time x minus x1 times xi plus 1 minus xi over xn minus x1 minus this term plus xi. Now, this term we are taking as ai. So, Li of x one can get ai time x. If you are finding here, you can cross multiply this term with here and the common denominator you can multiply this term inside. So, one can get minus x1 xi plus 1 minus x1 minus plus x1 xi plus, if you are multiplying this one xi xn and minus x1 xi over xn minus x1. So, which is equal to Li of x one can get ai x minus, here this two term will cancel. So, one can get plus xi xn minus xi plus 1 x1 over xn minus x1. So, this we can call it as bi, this we can call it as bi. So, this is in the form of Li of x equal to ai x plus bi. Now, one can understand what is the nature of this ai. This xi plus 1 minus xi is the interval of the length of the subinterval, where xn minus x1 is the length of the whole interval, this one. Then obviously, xn minus 1 is greater than or equal to xi plus 1 minus xi. Therefore, this term is always strictly less than 1, always strictly less than 1. So, that ai is acting as a scaling factor. That means, ai if you are applying on this interval x1 to xn is just compress the whole interval into smaller piece. That means, this Li is a contraction with the factor ai between 0 and 1, open 0 and 1. It acts as a contraction factor. Then what is the role of this bi? Bi is after contracting the whole interval to smaller thing, it just shifting whether left side or right side based on the points. So, that this point BI is acting like the translation or shift. So, generally BI, if AI is Li of x is defined as Ax plus Bi, then Bi is one can write as Bi equal to xi minus Ai x1. It ensures that the map is correctly positioned so that the left endpoint is preserved. That means Li of x1 equal to xi. That means Ai contract the whole interval, and this map, this term Bi adjust that this endpoint condition must be satisfied. Like that it will adjust the interval. Now can graphically explain the here. See, if we have the x1 here and x1 here and xn here, if you apply Li on this function, that Li on here, then what is the role of Ai? Ai just compressing the whole interval here, then this Bi just shifting whether left side or right side, adjusting, and Li just shifting the terms in the left side or right side, so that the endpoint should match with the endpoint of the subinterval. So, this can be explained by a simple example. One can get x1 as 1 and xn as 3. That means consider this interval 1 comma 3. So, in which we can consider the subinterval 1 comma 2. This is our 1 comma 3 and 1 comma 2. Now, we need to find the suitable Ai and Bi such that this 1 must map to 1 and 3 must be mapped to 2, then the remaining points between 1 and 3, it will be mapped to the in between 1 and 2. So, for that, for computing Ai and Bi, we can use this formula. Ai, one can use Ai is length of the subinterval divided by length of the whole interval. So, length of the whole interval is 3 minus 1 is 2, and length of the subinterval over length of the whole interval. So, length of the subinterval is 2 minus 1, it is 1, length of the whole interval is 3 minus 1, it is 2. So, Ai equal to 2. For finding the Bi, we can use the formula which is obtained here. That means xi xn minus xi plus 1 and x1 over the length of the whole interval x1. So, which is equal to, the denominator is, the whole interval is 2, the numerator xn is 3, xi is 1, xi is 1, and minus xi plus 1 is 2 and x1 is 1. So, one can get again it is 1 by 2. So, therefore, we get the two map, Ai value as 1 by 2 and Bi value as 1 by 2. Therefore, we are getting Lix plus Li of x equal to 1 by 2x plus 1 by 2. Now, we will see what is this map, role of this mapping when it maps to the interval 1 comma 3 to 1 comma 2. So, actually this time 1 by 2, the contract the whole interval. If you are taking the interval 1 comma 3, if you are applying the Li here, first initially this 1 by 2 compress this one as 1 over 1 by 2, we can get 1 by 2, and when you are applying 1 by 2 on 3, then you will get 3 by 2, will get this map. So, now this interval is like here, this side 1 by 2 and 3 by 2 is here, 3 by 2 is here. Now, what is the role of this Bi? Now, Bi making the shift from 1 by 2 to 1 and 3 by 2 to 2. So, now if you are adding 1 by 2 with this 2 interval, 2 endpoint of this interval, then it becomes 1 by 2 becomes 1 and 3 by becomes 2. Now this bi shift the contracted interval to the right side, so that the endpoint condition will match, and 1 map to 1 and 3 map to 2. So, it is the graphical representation is given here. So, when you are applying the AI and scaling, so it will compress the interval, and after applying the bi it will match exactly 1 comma 2. So, 1 maps to 1 and 3 maps to 2, one can get this figure. Now, so for any interval, if the closed interval is given, we can always find a contractive homeomorphism between the whole interval and its subinterval. You can observe that this Li is always it is a continuous function. Li is a continuous function. Then one can observe that the inverse will exist for the inverse always will exist, and inverse also continuous. This function is 1 1 and on 2. So, by using this formula, one can find the contractive homeomorphism between these two interval, and observe that this x1 and xn is mapped to the subinterval. That means, if you have the whole, then it is mapped as the compressed as the smaller image. This is the basic property. When we constructing the fractal, we need smaller parts, it must represent the whole thing. So, we are starting with slowly to build in the x direction. Now, we completed in the x direction for finding the interpolation function. In the x direction, we defined this Li from I to Ii is a contractive homeomorphism such that this L maps the I to the its subinterval Li. Now, this is acting in the horizontal lines. Now, we have to move on the vertical direction. In the vertical direction, let us take x as the I cross a comma b, where I we already defined, where I is a closed interval x1 comma xn. Then what is a comma b? A comma b is the a less than minimum of yi and b is greater than the maximum of yi. Why this condition? We are taking a and b particularly like this one. Suppose in the given point, suppose this type of points are given. Suppose this is my x1, this is x2, this is x3. My y1 is here, y1 is here, and y2 is here, y3 is here. So, here among all, we cannot take the interval a comma b as y1 to y3. If you are taking this interval, then this point will be ignored. So, that we need to take the minimum among all the y, that must be a, and take the maximum among all the y, then it takes to be b. So, that all the point will be covered in the rectangular region. So, we are taking I is a x1 to xn. So, it will cover all the points in the x direction. For covering all the points in the y direction, we need to take closed interval a comma b, where a is the lesser value than minimum of all the y, and b is the greater value among all the maximum of y. Now, you can note that I is a compact interval. So, it is a compact set, and closed interval a comma b also compact. Obviously, both are complete x is a complete matrix. We can use the Euclidean distance here, then one can easily understand x is a complete metric space with respect to the Euclidean metric. Now, define Fi from x to closed interval a comma b such that Fi is continuous mapping and satisfying the following endpoint condition. Also, F is contraction with respect to the second variable. Fi is continuous mapping satisfying this condition. Also Fi is contraction with respect to the second variable y, not with the first variable. It is contraction with respect to the second variable. That means if you are taking two different element in the second variable, then y and y dash, if you find the distance between xy and xy dash with respect to the mapping f, one can get it is less than or equal to ri times y minus y dash, where r lies between 0 and 1 because it is the contraction factor. So this function Fi is contraction with respect to the second variable. Also Fi satisfying this endpoint condition. So already we have seen Li of x1 satisfying xi, and Li of xn we can write xi plus 1. Here in addition to the horizontal line, in the vertical direction we are adding Fi of x1 and y1 equal to yi, and Fi of xn and yn equal to yi plus 1. So this is in the horizontal direction, this is in the vertical direction. So Li satisfying this condition and Fi satisfying this condition. So this condition makes sure that there is no discontinuity in the horizontal line, so that the whole interval mapped to the sub interval, the end point will be matched. The next while map, if you are applying L1 and L2, there should be no gap. Similarly, in the horizontal direction, Fi do the same job, it satisfying this endpoint condition. Now we have the two mappings Li and Fi. Li is contractive homeomorphism on horizontal direction subinterval, it is controlling the horizontal direction. Fi is contraction with respect to the second variable, it is controlling the vertical direction. Now let us define the contractive mapping Wi from x to ii to r. You can note we are defining ii. So Wi, if you are taking W1, if it is a mapping from x2, x1 to x2 cross r. We have n minus 1 number of mapping in the Fi and Li whenever n number of data is given. So this W1 act on the first subinterval. What is x? We know x is a I cross a comma b. The x is I is x1 to xn cross closed interval a comma b, and this one, the codomain, the image is x1 to x2 cross r. This is W1 in particular. That means the whole interval compressed to the subinterval. So that means this part, that means this Li is controls the horizontal direction. That means it maps x1 to xn to this interval, and this map Fi controls in the vertical direction. This will maps to the here the that means the subset of R it will map, so that the Wi will map to the whole rectangular to the sub rectangulars. So now one can show that if Li and Fi is contraction mapping, then Wi becomes the contraction. Then you can see, then this Wi also satisfying the endpoint condition, because this is one can verify easily that Wi of x1 and y1 can be written as Li of x1 comma Fi of x1 comma y1, which is equal to Li of x1 is xi and Fi of x1 and y1 one can get xyi, and in similarly Wi maps the endpoint of the whole interval y xn to yn as Li of xn and Fi of xn and yn. One can get this Li of xn is xi plus 1 and Fi of xn yn one can get yi plus 1. That means this mapping W maps the endpoint of the rectangular to the endpoint of the sub-rectangulars. That means the whole rectangular region will map to the initial point. If you are taking the whole rectangular, it will map to the sub-rectangular initial point. If you are taking the endpoint of the whole rectangular region, it will map to the sub-rectangular region's endpoint. So, Wi forms the contraction mapping. Now, we have n, if the n number of data is given, we have n minus 1 mappings. Now, this X is a complete metric space. In particularly, this all the Wi's are contraction. Now, we have the complete metric space and contraction mapping. So, this is our X and this is our Wi, where such that I belongs to n minus 1. There are n minus 1 mapping. Now, this will form the iterated function system. More precisely, this iterated function is a hyperbolic iterated function system. Okay. Now, we can define the Hutchinson mapping on the iterated function system. So, I can call this iterated function system as F. Iterated function name as this F. Then this F denotes the Hutchinson Bansley mapping from the hyperspace of X defined by f of b equal to union of all the contraction mapping. So, that means f of b equal to union of Wi of b, where each Wi is a contraction mapping. Now, as per the iterated function system, this f has a unique fixed point. That unique fixed point we need to establish as it is a fractal interpolation function which passing through the given set of data points. That we will discuss in the next lecture. So, the goal of the next lecture is to find the fixed point of the HB mapping F on the complete metric space H of x. This is our next goal. Thank you. Here it is the references. One can refer the M.F. Barnsley for more details. Thanks.